All right, so in this recording, we're actually going to locate the files and run through this example in LiveLand. So again, I will log into my remote connection. Maybe not today. We must be at one of the hours where it's resetting itself. See, it does it to me too. Huh. Usually doesn't take this long to regain control. We'll take a few minute break. I'm going to pause the recording temporarily. Recording. Okay, so I've resumed the recording. For future reference, the browser occasionally drops the connection. I had to exit the browser and restart everything, and now we are a happy camper. I have the example, and I'm on my remote connection. And now we have to attempt to find the already built files. So I'm going to guess that I named it Water Quality Example. Not a very good image for the image viewer. But I think this is the correct example, so that's one we'll load. File, open, WQ example. Shape looks about right. Let's bring in the background. Yeah, it's pretty much the same. We attempt to do an alignment, they line up. So this is the same problem. I'm going to turn off the background because we don't need it. And I'm going to recenter this. Okay, there's our base setup. Let's go look at what we're trying to simulate. So this first pipe up here, going from point A to this point, is 6,000 feet, 16 inches. Let's go be sure that that's how it's represented in the computer program. 6,000 feet, 16 inches. It says the roughness is 110. So what that would mean is the hydraulic method is going to be Hayes and Williams. Sure enough, it is. That's a different loss model than we've been using. And our next thing is let's go to options, times. This is set for a 24-hour simulation. Hydraulic time step of 1 minute, quality time steps of hydraulic time step of 1 hour, quality time steps of 5 minutes. We'll change that in a little bit to see if it has any impact. If we go to the quality, the parameter we're mapping is called Freddy Krueger. Let's just call it chemical. So I'm renaming it to chemical. It's in milligrams per liter, but there are other choices. You can do micrograms. Diffusivity, we'll keep that as whatever the default is. If we go to the reactions input, we have a first order reaction in the bulk phase, first order reaction at the wall, the bulk coefficient is -5, which was given in the problem statement. So these are non-trivial numbers. You can't just make them up. The -5, normally you would actually collect real data in order to determine what the bulk coefficients are. There's not a whole lot of literature support for coming up with these numbers, and that's why I said earlier the modeler has to be very comfortable with chemical modeling to be able to operate this effectively. I'll leave everything else as the default zeros. And I think we're set up to go. So let's go ahead and run it. So if in our nodes we have a choice of chemical as an option, so we can map that, and it says that our initial condition, there's no chemical anywhere in the network except it should be that should be a 10. I must have made a mistake. Okay, now the chemical value is 13 here, and it's propagating throughout the system. Let's go ahead and correct it because we have a mistake. Okay, so we built the hydraulic model. We messed with reactions. We messed with times. We need to go to the reservoir and set the source correctly. So we would go to the reservoir and set the source is currently set at 13. Let's set it at 10 because that's in the problem statement. Press OK. Rerun the simulation. And now when we start mapping results, it should make more sense. That should become a 10. Makes sense. 9.96. These two are still 0 over here. And think what's going on. This point right there is 12,000 feet. So that's 2.5 miles. About 4 kilometers. Yeah. So it's 4 kilometers away. And it hasn't had time for the chemically modified water to get over here yet. So in the next hour, depending on how fast the water is moving, in the next hour some water arrived and now we have a concentration of 5. In the next hour a little bit more has arrived. We still don't have any at this point yet. And now finally that point is receiving concentration. And we go to there, and that's the map of concentration. And we can actually go to that node. Time series, chemical. So there's the chemical for node number 6. Now let's modify the time step. Options, times. We'll go to 1 minute time steps. Let's see how fast this So this stuff is moving 1.5 feet per second in our model. So at 1 minute time steps to go 6,000 feet, it's got to run almost 3,000 seconds, which is quite a few hours. And I'm just going to go pick that one. Chemical. So hour 0. That chemical gets to its peak value of 8 and stays there after a couple hours. If we go to this remote node, make the same kind of plot. Same shape, of course, but it's now taking 5 hours to get there. So that's your basic water quality calculation. Now, if we want to consider water age, because we switch to a 0 order reaction, Kb equals 1. So options, reaction, zero order, even though these are all set to 0, we'll do that anyway. 0 order, and it says set Kb equal to 1 or minus 1. Kb equals 1. We'll change it from chemical to age. I think that's all we have to do. Now when we simulate it, when we plot the chemical, we're plotting the age of the water. Okay, remember what we did in the prior plot. It was somewhere between 1 and 2 hours at that point received its chemical, so we would expect the water age at this point to be between 1 and 2 hours. And so at that particular node, the water age after 1 hour is 1. The water age after 1.1 hours is 1.1. And
can you give me a minute? Only 1 minute. Because there is emergency call.
All right.